I'm Katie Miller, and today we are going to be talking about the maximum angular velocity of a cylindrical container before a liquid spills. So basically what we're talking about is we have a cylindrical container and it has some fluid in it, and we are going to want to spin the cylindrical container fast enough that the water gets right to the edge but doesn't spill over. So what this looks like, what we start off with is the container with some fluid in it, and the initial height of the liquid is going to be equal to the radius. And this is one of our assumptions, and we are doing this so that the math is a little bit easier, because if it were different, it would be much more complicated. So since we have this, we can say that H is equal to R. And then when we spin this container, the fluid is going to take a parabolic shape. So it's going to come up to the total height of the container, which we are going to call capital H. It's going to come right up to the edge, but not go over. And so when we do this, we are spinning with an angular velocity that we are going to call omega. And so when we do this, the fluid goes up and it touches the edge, but it doesn't go over. And so we want to solve for omega in the end. And so how we're going to do this is we're going to start out with an equation. dP over dr is equal to the density times the angular velocity squared times r. And so this little r is going to be a radial point. And so it's going to be somewhere along this radius. Doesn't really matter where, but that's what the little r represents. And so what we're going to do is we are going to take the integral, and to do that we want to move the dr over to this side, and what we end up with is the integral from 0 to p of dp is equal to the density times omega squared times the integral from 0 to r of r dr. And when we solve this out, we are going to find that P is equal to the density times angular velocity squared times r squared, and all of that is going to be over 2. So now we're going to talk about, when we spin it, how the height of the liquid changes. So if we look at this, this represents the initial height of our liquid, and we can find one point, and we are going to call this H. And so H corresponds to a radial point. And so we can define it as H is equal to omega squared times r squared, and all of that over 2g. So if we know this, then we can define when little r equals big R, which is our total radius. So we can say H when little r is equal to big R, and this is going to be equal to omega squared, big R squared, all over 2g. And so now that we have this, it is all relative to the dip in the parabola, and we need to find the initial height of the liquid to end up finding the angular velocity. So I'm going to draw out some diagrams. So we have our initial state, and this is our fluid, and this I'm just going to fill in with dots, and it's going to be equal to the volume of this, which I'm going to represent with this. And so we know that we are not losing or gaining any liquid, so we know that the volume of this space has to be equal to the volume of this space. And so what we can do is we can write out that pi r squared times d, and d is going to be this height, so it's going to be the total height of the container minus the initial height of the fluid, and that is going to be equal to the volume of this shape. And to find the volume of this shape, we are going to want to write out an equation. It's going to be R minus D plus H R equal to big R equals the total height of the container. And so now we want to solve for the volume of this. And so how we're going to do that is we are going to have the integral from 0 to v initial of dv, and this is going to be equal to 2 pi integral from 0 to big R of hr dr. And so when we solve this out, we are going to end up with v equal to 2 pi times the angular velocity squared over 2g, and all of this is going to be multiplied by the integral from 0 to big R of r to the cubed dr. And so once we finally solve this integral, we are going to end up with v equal to omega squared times pi over g times big R to the 4th over 4. So now that's what we have for the velocity, or not the velocity, the volume. And as we defined before, the volume is equal to pi r squared times d. So we can substitute that in and say pi r squared times d is equal to omega squared pi over g times r to the 4th, and we can put the 4 from here down with the g. So this is what we have, and we are going to find d for it. So we can solve for d, and this is going to equal omega squared r squared, all of that over 4g. So now that we have d, and we have v, we can plug in the d into the equation that we had before, which is r minus d plus h r equals to r times h. So to do that, I'm going to erase the board. So we have r minus d plus h r equals r equals capital H. And so we have d, and we already defined h, so we can plug all of that in. So we end up with r minus omega squared r squared over 4g, plus omega squared r squared over 2g, which we defined as h before. And this is what we have. So what we want to do from here is we want to get r and h on the same side. So we're going to end up with h minus r is equal to omega squared r squared over 4g. And so once we have that, we are going to want to solve for the angular velocity. So we're going to end up with omega squared is equal to 4g times h minus r, all of that over r squared, and then we're going to take the square root, and we end up with omega is equal to 2 square root of g times h minus r, all over r. And this is the final equation that we get for our maximum velocity, and you can get all of these values from the difference in your container, so we can find the height of the container, we can find the radius easily, and we can plug in those numbers and we can get the maximum velocity before the liquid spills. Thank you.